Okay, so we had this problem last time. We had how many bins?
Six.
Six?
Six car problem.
Here's six, and here's a movable partition. And we had a particle A here, and then three on this side or two? Two. It'd be C, like this. And we were only single occupancy in a bin. And so what we wanted to do is we wanted to start with the partition here and look at how the degeneracy changes on the left and on the right for each of these here. Evan, sorry, I thought you were at the Florida meeting. Isn't there a CMC something? No. Okay, there is. Okay.
I'm just getting over sickness. So
So here's our left, G left. I'm just looking right at it. And so let's just do a little review. When we had this, recall last time. From episode 4. You call that degeneracy. That was actually, it was nominated for several Emmys and stuff like this. Best screenplay, best acting.
Really
It
should,
was brilliant.
really should run more.
It was fantastic. We had a whole bunch of bins here. Let's say we have N bin. And then we're going to put in a certain number of particles that were, let's say there's an A here, and there's a B here like this. So we have, let's say we have 4. So number of bins here, 1, 2, 3, 4, 5, 6. We have, so this is 6. We had 4 slots. Okay. What is the degeneracy of this here? What did we say? What did we think the slot? We said the slots could be filled with what?
Invisible walls.
Invisible walls. Okay. So if these were all, let's say this was an A, B, C, D, E, F. Let's say it had 6 distinct balls. Okay. How many? What would be then the degeneracy that I could rearrange this? In other words, total number of permutations.
6 factorial.
Maybe 6 factorial. That makes sense. Then we said, what happens if we make 3? Let's say we take 4 of the balls and we make them blue, and then what do we have to do? Or yellow or green? We make them all one color. Then you'd have to divide by. We would have something like this. So let's say I had a C, a C, a C, and a C like this. Then what would happen that this would be overcounted, because what I could have is I could have the case of C1, C2, C3, C4. I could have C2, C1, C3, C4. I could have all these combinations here, right? And they're all look the same. Now, how much would this be? This would be 4 factorial. So for any combination I would have here, is going to be overcounted by 4 factorial. So to fix it, what did we do?
By 6 factorial.
We divided by the 4 factorial. And then we said, well, instead of having a C, 4 C balls, let's say we painted with invisible paint. So it looks like an empty slot. What do you end up with? The exact same answer like this. Okay. And so what we did is that we looked at the position of the partition. I just want to go over this point because I really rushed it last time. And the position of the partition here. Oh, let's put it here. And so what could we do? We could have 1, right? The partition could be here. It could be the first spot, second part, third, fourth, and fifth. And then I could look at G on the left, G on the right, and then G total. Okay, so what did we say would be the partition if it's over here? That would have, this would just be 1. Okay, so this would be 1. Now, if the partition is here, okay, what would then be the degeneracy then on the right?
5 factorial divided by 3 factorial.
Does that make sense? Because you have 1, 2, 3 empty spots, and we have 5 things here. So this would have to be 5 factorial, 3 factorial, which is
20.
Okay. Now we put the partition here. Okay, so what's the degeneracy then? 2 on the left. If it's here, what's the degeneracy on this side here?
4 factorial divided by 2 factorial.
Okay, so this is 4 factorial over 2 factorial. And that gave us, and if we put it 3, if I put it here, then what would happen?
3 factorial on left divided by 2 factorial.
Yeah, this would be 3 factorial over 2 factorial. That, which is 3. Then this side over here.
Factorial over 1 factorial.
Okay. So you'd have just 3, it would really be, it would be this over the 1 factorial, which would just be, no, identical. 6. Then 4.
It would be 4 factorial over 3 factorial.
Yeah, so this would be 4 factorial, 3 factorial, which is 4. Then on this side here, so it'd be the 2 factorial. It was 2. Can I have a 5?
No.
No, this is not allowed. So I really don't have any idea why I wrote it there. So this is not allowed. Because, yeah, we said there's only single occupancy in a spot here. Now, what did we say then is going to be the total degeneracy for this entire system?
GL times GR.
It's a product of these, so we multiply these two together. So this is 20, this is 24, 18, and 8, like that. And then we made a graph, and the graph I did a really crappy job on, so I wanted to do the graph better because it was just really awful. I should have looked at my scale. I'm going to plot my G here. This is going to be G left, G right, and G total. And this is going to be basically the position of the partition. Let's make this a little bigger. This is 1, 2, 3. Okay, so how does the G left look? It's just 1, 2, 3. So let's come up with a scale here. If you make this 10, that looks like 20. This looks like 15. That looks like 5.
You should probably go a little higher since you have a 24.
Ah, thank you. Okay. And that looks more or less, it's okay. So what would this look like? This would be a 1. I'd put this one over here, and this would be 1. And then I'd have a 2, so I'd come over here, I'd have a 2 here like that. There's a 2. This is already looking bad. 3. Okay, and then 4. Okay. It's better than what I had last time. So basically we're going to have some graph like that. I wouldn't connect the dots here, but that's okay. It would be something like this. Okay, so this is going to be my G left. Then what did we say G right looks like? Yeah, it's going to be the 20. So we have at 1, we have a 20 here. And then we don't have that. Yeah, 20. And then we have 12. So from down here, this is going to be 12. That. And 3 is going to be 6. Close to that. And then that 4 is going to be a 2. So it's going to be something like this. So this is going to be something that kind of goes down like this. Actually, quite severely. So this is going to be my G right. Does that make sense? When you multiply the two, what happens here? You get a 20 here. So this is going to be 20. And then at 2, what do you get? You get 24. So you're going to get this. And then you get 18, which is going to be like here. And then 8, which is going to be here. So you're going to get really the total is going to be, well, this is my G total. Now, what did we say? This is a microcanonical ensemble. What does microcanonical mean again? Number of particles stays the same. Energy stays the same, and then the overall volume here will stay the same. And again, and these problems here, I have to turn off the interactions because if there are interactions, then it would mess up all the things. So basically, all the states here have equal energy. So what do we know about any one of these given states? Any one of these given states would be called a microstate. And what do we know about all the microstates? They would all be equally probable. So where are you most likely to find this here? So this can be anywhere here.
Position.
Yeah, you're most likely to find this position here. And why? There's nothing magical. It's just that this, more ways to be this way. That's just all there is to it. Okay. Again, this is going to be the macroscopic property. Because what you do is you look at macroscopic properties. You can't look at, usually when you have 10 to the 23rd particles in your system, you can't say the quantum numbers of each of those 10 to the 23rd particles. If you can, there's been a technological improvement. a really, really, really profound one, okay? I can, okay, I'm good at 10 to the 22 particles, but 10 to the 23, I'm not good at. No, that's, you can't do that. Okay, does that make sense? And then I made it, kind of an interesting, well, it is an interesting point. We could actually look at the number density here. So what I could do is I could call the volume of this. So call the volume of this. Call the volume of each cell. Delta V, for no good reason. Okay, and then we can look at the number density. Right, which is going to be your number of particles over the volume. Okay, so on the left, if I look at this number density on the left, what would it be? I have how many particles on the left?
Which position is this currently?
Thank you. Let's do it for this maximum configuration here that we're going to calculate this. So for max G total. So for the max G total, in other words, this is in the 2 position. Okay. What is going to be the number density? The number of particles is 1. And then the volume would be what?
2B.
2.
We would have 2 cells, so this would be 2 delta V. Now, if I look at then the number density, right. What would we have? We have how many particles?
2
2
over 4.
This is over 4 delta V. And so what we end up with is that the number density on this side equals the number density on that side. And that's not very surprising. Now, when we have this, when this is going to be actually the equilibrium configuration. When you make that bigger, this will be the equilibrium configuration here. And this makes perfect sense here. Because let's say this were actually gas molecules here. Okay. What would you say about this partition? Where would this partition end up?
It is.
Okay, you basically, this would be like a gas. So you use the idea of gas law. What would you say about the pressure on this side compared to the pressure on this side? You'd want them to be the same, and that's really related to the number density. I want to just show you all that, how that works. Okay. So we're going to drive this later on, and I'm just going to say it. So we call ideal gas law. PV equals nRT. Okay, a physicist will usually not write PV equals nRT. What would a physicist write? Yeah, let's go through and do it. So how do we calculate the number of moles? Number of particles over Avogadro's number. So when you're a kid and you get taunted like nah, 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 nah. What it's really not a taunt. It is the child's trying to tell you that basically when you grow up, you're gonna have to use Avogadro as a number. And so it's really basically it's a promotion for chemistry and stuff like this and scientific notation. We're learning a lot. Okay, so what do we then call this? That is the definition of Boltzmann constant. Okay. So if I take over my V, I get my number density times kBT. Now we have no idea of temperature yet, so the temperature is going to be fixed. Okay, so what's going to happen? Well, basically, if this pressure is the same, this pressure, the number density would also have to be the same. So you're getting this idea right there. But again, nothing magical has happened. It's just that there's more ways to be in this state here. That's going to be what happens with all statistical mechanics. There's just more ways to be a certain way. And if there's more ways to be that way, and if everything's equally likely, that's where you're going to be. Does that make sense? Questions?
I have a question.
Sure.
Yesterday lecture, you
Yeah.
were like that.
Well, I was trying to rush the class to get to that point. So don't that
Yeah,
diagram's
this
awful.
is like a.
That's crap. That's
Okay.
just an awful diagram. That's why I wanted to do this because that was I was rushing to that point. Any questions to that? It was really kind of a pretty little thing. Now, we defined something called microcanonical entropy as well. What was that?
ln G.
Yeah, so what's gonna happen is that as these number of particles get large, these degeneracy values can get preposterous. Well, see, again, if you have like 10 to the 23 factorial, good luck with that. You know, just you're gonna be calculating forever. Okay, so as n increases, n factorial becomes again ridiculously large. So we take the natural log. Okay, so we're going to say the ln of n of g here, like this. This is by definition sigma, okay, which is our microcanonical entropy. Does that make sense? How can I make it then? Usually, if you talk to like a chemist or engineer, they'll have S, they won't have sigma. How do we get an S?
Yeah, multiply by Boltzmann
We
constant.
multiply by Boltzmann's constant. So if you take this here and multiply by Boltzmann's constant, so you get this KB sigma. This is then S. It's just the so again, when you talk about entropy, you think of it as being of the randomness or disorder in a system, and that makes sense. This G is the number of ways you can rearrange a system. And if there's a large number of ways you can rearrange the system, that would actually manifest itself as disorder or randomness. But it's just how you can rearrange the system. That's all this stuff is. It's just counting. Does that make sense? Then we had a cute little thing for the first law, frequently called the second law. You add one to one for the second one. Then we had another little example of this. Let's say we have that. Let's say I have a particle here, A, B here, and particles C, D, and E like that. Okay. What would be my initial entropy for the system? How do we say we do that? Let's go through and let's calculate it.
Well,
Let's go through and calculate it. It might be 12, it may not be. I honestly have no idea. I can tell it's not going to be 12 though.
yeah, 2 factorial times 3 factorial.
What is S? What is sigma?
ln 12.
Okay, I might believe ln of 12, but not 12. Okay, so what is our G on the left? How many ways can I rearrange that? Just 2. Okay, our G on the right. Yeah, they're all distinct particles. This would just be 3 factorial. This is 6. And so our G total is going to be G left times G right, or 2 times 6, or just 12. So our initial system here, our initial sigma, is just the ln of this. It's just the ln of this 12 here. Now, what kind of neat thing did we find with that as well? What's another way to write that? If I take the logarithm of this, what does that also equal?
Oh,
Engineers and physicists.
ln of GL plus ln of G.
Thank you. Yeah, right. So if you take the ln of this guy, that's just the ln of G left. That's the ln of G right. So this is just my sigma on the left, the sigma on the right. That equals our sigma total. That's kind of neat. And what did we do? We had a nice little example of the second law. When we do that little partition, we took it out. So if that partition's removed, this. A, B, C, D, E. Okay. What is my G for the, what is my G? Just,
5 factorial.
this is 5 factorial. Okay. 5 factorial is. What I need.
On top of
60, 60, is it 60?
on top.
Or 120?
Yeah, one.
120. It's 120. And so our sigma final here, this is gonna be what? ln of 120. So what happened to our entropy? I had better. Oh, went up. Okay, did anything magical happen in the process? No, it's just there's more ways to rearrange the system. And this is what happens in the second law. That when you have something spontaneous occurring like this, what happens is there's going to be more ways to basically rearrange the system. And that's all the second law is. There's nothing really profound. It's profound, but if you look at it, you can understand exactly where it's coming from. Okay. Now I want to give you one more model. We're going to do two, but I'm going to want to say one about the homework, and then one about another model, and then I want to talk about something called the Stirling approximation. I'm going to give you a more general derivation of this. Okay. So in homework 1, question 1. You have 8 spin half atoms. Right? And I want you to basically, I want you to find the degeneracy versus net spin. By net spin, I mean the net number of spin. This net spin is going to be n equals n up minus n down. Okay. So you're going to make a little table here. I ask you for a table. So we have basically 1, 2, 3, 4, 5, 6, 7. So I can have something like this. So n is going to be 8. In this case here, what would be the number of spin ups?
6. Yeah,
5. 5. Okay.
there's only 2 spin down.
Are you sure?
Yes.
I got
Look
it.
at the last one.
1, 2, 3, 4, 5, 6. Yes, it is 6. Okay. Me count good. Okay.
I did the same thing.
Okay, number down is then 2. What would be the degeneracy of this? So the way we're going to write this, I'm going to write this as 2. I'll say 6, 2 like this. So I'll write the G is basically number up, comma, number down. Okay. How would you find this?
6 factorial over 2 factorial. Yeah. No. 6 factorial times 2 factorial.
6 factorial times 2 factorial. Everyone agree?
Factorial over.
Oh, I can't wait to find out how this works. I've always wanted to take this course. Take good notes. I can't wait to find out what we're learning. What is this nothing but? This is nothing but the atoms in the slot problem. How many little slots do we have here? 8. 8. Okay, if all the particles were different, what would we then have? 8 factorial. But hey, guess what? In this case, 6 of the particles are the same. So what would we do?
Over.
We would have to divide by 6 factorial.
And 2 factorial.
Hey, 2 of the particles are the same. What do we have to do? We have to divide 2 by 2 factorial. Okay, so what you're going to do in this problem here. Is I want you to make a table and then make a nice plot of it. Basically, you're going to have like the number up, the number down, and then the G here like this. Okay, so the first one would be what?
All
All up, so this would be 8, this would be
0.
0. Okay, oh no, let's have the net spin as well. We'll have the net spin, which is spin up, and spin down, so this is 8. Then we'll have the G this one. This What would this be formally? What does that be? If I use that formula here, what would that become? It'd be a factorial over. Okay, what does this represent mathematically? This a factorial is the number of particles. So this is really n factorial. What is this guy here? That's another thing about the n up factorial. And this is nothing but the n down factorial. So using this notation here, saying that this G is this. And what does this become? Let's do it formally. A factorial over 0 factorial. Okay. This is 1. Now, what does that mean about 0 factorial? Just in case you've never studied this before. 0 factorial by definition, and this definition is 1. Now, why is 0 factorial by definition 1? I'll give you a hint, you now know. Well, that's exactly what, this won't work if you don't have 0 factorial equaling 1. It's entirely defined by this. That's entirely why that 0 factorial is defined to be this. Okay. So you're gonna plot all these here, and then you're gonna make a nice little handy dandy graph. You're gonna plot them this G, and then this next bit. Okay. You're gonna plot that. And what did we say happens? As that n becomes larger and larger and larger, what's gonna happen to this? Remember, initially, what do we have? If we had a small number of particles, oh, you should yell at me here.
Ah,
Okay, plus 1 for him. I was sloppy. I criticize Colin for being sloppy sometimes, so I have to take it as well. Define something to be a distinct variable. What did I define? It's sloppy on my part. What did I say n is?
oh,
The total number of slots, the total number of spin up and spin down particles. Okay, what did I call this over here? The same thing. Okay, so what I'll do is I'll put a little hat on it. A little face. It's different now. And this is what we're gonna plot. Okay. So what did we say happens when the number of particles is small? You're gonna get something kind of broad like this. But as that number gets larger and larger, what's gonna happen? That's gonna narrow up and go like this. And as that n starts going towards Avogadro's number, you're gonna get something like this. It's gonna effectively look like it's gonna spike and go like this.
Does it turn into a direct delta function?
Actually, it does. Okay. But we don't know that word yet. We're gonna do a lot more direct delta functions than you probably have done before. So, what does that mean here? Could you ever find let's say we have a really Avogadro's number. Could you ever find the system here?
yes.
Yeah, but I can go and buy one lottery ticket, and I don't think I can then say, I'm not gonna go to Mark Zupan and say, Mark, I'm retiring because I bought a lottery ticket. My future is, I'm now secure. No, not a wise guy. Okay, so in principle you could, but it's really misleading. And so what's going to happen? Your system's going to be here for all practical purposes. And what is this? This is going to become the equilibrium state. So when you do traditional thermodynamics, your system is very stable. Why? Because basically your system is only here. Okay, but what we're going to be able to do here, we will worry about some of the little fluctuations about that. And we'll get rise to correlation functions and stuff like that we haven't done yet. Okay, that makes sense? Okay, so that'll help you at least organize what I'm intending for that problem. Now, that said, let's look at another. Well, let me do one other thing. Let me talk about Stirling Clark solution. Then I'll do another model for you. How can we approximate the ln of n factorial when n is negative? Okay. what I did is, I'm gonna give you the version that we're only gonna use in class. And I must say, it's about the only one that I've ever seen used a lot. I've handed out the derivation of the more general one, and it turns out the derivation of the more general one is straight from hell, and for a really dumb correction factor. Here's something that's really, really tiny. So I'm not gonna worry about it, because the correction factor is just way, way, way too involved to get. I mean, for considering you're not gonna use it. If you used it all the time, I would do it, but you don't. Okay, so what we're gonna do, the answer to this is gonna use the Stirling approximation. Okay, and this is gonna be the ln of n factorial is approximately n times ln of n minus 10. And I want to show you where that comes from. It's actually quite cute. I'll put a little note here. No. Occasionally. Okay. You might need a more refined approximation. To ln of n factorial. And that is, and if it's so refined, I've used it maybe like once or twice in my life. It's really this equation 12b on the first page of that handout I gave you. It's going to be this. It's going to be 1/2 the ln of 2 pi, okay, plus n plus 1/2 ln of n minus n. In fact, this plus 1 over 12 or 12 to the n is almost never used.
Let's put the 0 to the 1 to the n.
Okay, if you look at this equation here,
0.
okay, I'll put a little thing. So this would be plus, not that at all. Here. Okay, so this right here, oh mess. Now this right here, what does this mean here, that 0?
No, it's not 0.
It means order. So this would be, this right here means order. And it means that there's going to be a term that's going as 1 over n squared. All this means is there exists. I really like saying there exists. It makes me seem like a mathematician. There exists.
Why would you want to seem like a mathematician?
I married one. Okay, so there exists a term. You heard the joke about the what is that? Mathematician, engineer, and physicist, and the fire in the basket. So there's a physicist and an engineer and a mathematician in a room, and there's this fire going on, and there's a desk with water here. And then the physicist writes some theoretical proof of basically, what to do. And the engineer comes up with this other stuff of what to do. And then the mathematician looks at it and says, a solution exists. Okay, so let's see, there exists, okay, a term going as 1 over n squared. Now, if n is large, what can we then do with that term? Let's get rid of it. So you're going to get rid of this term, you're going to get rid of this term, and you're going to have this here. Now, how do you go from here to here? If n is large, right, this 1/2 doesn't matter, right? If this is 100, 100 plus 1/2. Okay, now this term here is on the order of 1, so we can just chuck it. So normally, kill that guy, you're good. Okay, I want to show you where this comes from because the proof is actually not hard. Okay, we have the ln of n factorial. So if I were to write this, how would I write that formally? The ln of, what's n factorial mean?
Times n minus 1.
Yeah, so it'd be n times n minus 1 times n minus 2 all the way down to 1. Okay, what can I do with that? Yeah, this is the ln of n. It's the ln of n minus 1. It's the ln of n minus 2. That's all the way down to the ln of 1, which I know is 0, but. Do I have another way to write that? No. All right. Yeah, it turns out you can't. Proof's done. Proof's too hard. Okay. Time for lunch. Right, let's kind of read it this way. It'd be the ln of 1 plus the ln of 2 plus the ln of 3 plus the ln of 4, all the way up to plus the ln of n. It's a sum. So I could really write this as a sum. I'll say ni 1 to n of the ln of ni. That makes sense? Now, let's review our 4 most important math techniques. What are our 4 most important math techniques in physics? Multiplying by 1 in a clever fashion. Adding 0 in a clever fashion. Taylor expansion. Not a bad one.
Separation of variables.
Separation of variables.
Pretty much.
Okay,
That's the-
so what we're going to do here to solve this. Brilliant. We're done. Okay, now what can we do with this? I'm going to plot basically my ni axis here. So this is 1, 2, 3, 4, 5, all the way up here. I'll over this like this, then here like this. Yeah, so this is the ni axis like this, and this is going to keep on all the way up here. Then what is the separation distance between any one of these values here? 1. Crazy. It's 3 minus 2. 1. Whoa. Okay. 4 minus 3. It's 1. Okay. So what I can do is I can write this 1 here. I can really call this kind of like delta ni. Well, that delta ni is really going to be this, ni plus 1 minus ni. It's just basically the difference between any two of those values there. So I can then write it like this. Now, why did I write it like that? What does this like suggest above? It looks like a Riemann sum, right? So this looks like a Riemann sum. Yes, it is. Okay. And so what I can do is I can say that then this is approximately the integral from 1 to n of the ln of n dn. Or if you want an x there, that'd be fine. You could do it like this. If you want, I could have an I in here like this, but it doesn't. I can put an I in there. Okay. Now let's go back to those halcyon days of Calc 2. What is the logarithm of, not that at all. What is the integral of the logarithm of x? Recall. You don't really get this integral a lot. The integral of the ln of x dx is x ln of x minus x.
Wow.
Okay, crazy. Okay. So what do I get? I get ni minus ni from 1 to n. And what is this? This is going to become n log of n minus 1 log of 1 minus 1. Log of 1 is 0. I get a plus 1 here. What am I going to do with that if n is large? Done. Okay. And so what we get here is then this is approximately this n log of n minus n. Kind of slight. Kind of slight. Does that make sense? Let's get one more model. Then what I want to do next time on tomorrow, what I want to do is I want to actually show you the formal definition of temperature in terms of basically how the entropy changes with respect to energy, which sounds bizarre. And I want to show you then a more robust definition of our understanding of the second law. Let's go on with our model. Any questions with this? Make sense? Okay, so let's see what we have here. And again, you could say, well, how does that one become a dn where d is small? Again, n is large. So if n is like Avogadro's number, what is Avogadro's number plus one?
Basically, I've got it.
Yeah, so if I look at Avogadro's number here, and Avogadro's number plus one here, I think it's very safe to call the difference between these two dn instead of just one, even though it is technically one. I think it's very safe to call it, dn. Okay, so one more model.
Just one more model.
We're actually gonna have two more, but this will be. Let's have distinct particles. With multiple occupancy. Okay, so what I can do here, maybe a situation like this, where we have our cell or 1D box again. Okay, I can have particle A here, I might have particle B here, I might have C, D, and E here like that. Okay, so same situation as before. They're distinguishable particles, but then what happens? I can let the particles be anywhere. What do you think our last models will be? It has to do with the distinguishable.
Indistinguishable.
They're going to become indistinguishable. Exactly. And then the indistinguishable particles that can be multiple occupancy are going to become our buddies, the bosons. And there are particles which are indistinguishable. I mean, they're indistinguishable, but not multiple occupancy are going to become our buddies, the fermions. You don't need a lot of that stuff a lot often, but what happens is if you go to glass conferences, you'll hear a lot about the boson peak. And what is this boson peak talking about? Well, it turns out it's tied in with these ideas here. Okay, so let's figure out how to do this. So let's take a simple case here. I'm going to give you the answer, then I'm going to prove it. So the degeneracy force. So the question is, what is G? What G is going to be, where we have basically distinct particles, multiple occupancy, it's going to be the number of slots, number of bins or slots, times m, which is going to be the number of particles. And the
To the power of instead of times.
what?
To the power of instead of times.
To the power of it. Yep. And I'm going to do a proof with cartoons because I think that actually makes more sense to me. At least in my tiny little brain. So what I'm going to do is let's take 4 slots. Oh, let's take 3 because I don't want to draw anything with 4. Okay. So let's take 3 slots. 2 particles. Okay. Now I'm going to make it a little grid here. What I'm going to do is up here, I'm going to draw the particle A in each of the slots all by themselves. So I have this little picture here, I have 3 slots, this little picture here, 3 slots, and this little picture here, 3 slots. My buddy A can live here, my buddy A can live here, my buddy A can live here. Now I'm going to do the exact same picture, but I'm going to repeat it for B going down here. I can have B here, or B can be anywhere. So what I'm gonna do is now I'm gonna imagine if these are like pictures, I'm gonna imagine superimposing the pictures on top of each other. So if I take this picture and add them together, well, not superimpose them on top of each other, what would I do? I'd have A here and B here. If I go over here, what would I have? I'd take this one and then this one, I'd have this one. And then this one and this one. I have that. I could do that for each of these here. If I come over here, and this would give me this one. This one, that. This one here would then give me A, B. And then this one here would then give me B, A. And I have to complete this, or otherwise I just won't feel complete. Okay. Even though you get the idea, it's just it has to be completed. A, this is B. This is A, B. And this is then B. How many do I have here? I have 9. How did I get 9? Because I have how many slots? I have 3 slots. Okay. If I had 4 slots, what would I have to do to this? I need another column. If I had 5 slots, I need another column. In the same way down here. Okay. Now, how many axes here? I have 2 axes here. Why? Because I have A's that could go here. I have B's that could go here. So this is going to be really 3 times 2. Now, what would happen if I had 3 slots with 3 particles? I'm not going to draw this. Okay,
Yeah.
we're going to act it out. Okay, what is the marker? What would I need? I need another a third axis. So I'd have a third axis here like this, and I'd have those exact same pictures here. But what I do, I'd have C. I'd have the corresponding picture for C here, C here, and C here. Then what would I do? I multiply them out. I get this grid thing. Okay. And then what would I have?
There's still 3 slots, you have 27.
I have 27. Does that make sense? Okay, to me, I like that for mathematician or not, because well, there's probably there's not this symbol, there's not this symbol, there's not this symbol, there's not this symbol. Put those in there and then that's what you have to do.
Maybe those are your particles instead of A and B.
You need these here. Okay. I don't know if this symbol means. There exists. What about this? Or yeah, for every or whatever. So my wife gave me a joke once when I went on an interview. I went over well. What is this? For every upside down A, there exists a backwards E. Of course. Go ahead. Go ahead. So now what can we do? We can do exactly those same problems that we had here. In other words, this homework problem that you had here. You do this exact same problem here, but now you could just repeat it now for basically multiple occupancy. But it's the exact same physics. Does that make sense? Okay. So we'll do another one. I want to set up something, and the clocks are getting to me in this room. Actually, it's 12:11. It is 12:11.
I think.
Okay, well, I guess technically class is so we'll stop here. What we'll do next time, though, we're going to take 2 systems. We'll take this system to have energy E1. We're going to put it in contact with the system here, E2. Now, what I'm going to do is let the energy go back and forth between those systems. Okay. And what we're going to find out is what eventually happens to that system. Right. At some point, this is going to have some temperature, and this is going to have some temperature. Eventually, what's going to happen? They're going to have the same temperature. And it turns out it's going to be entirely related to basically entropy, which is a completely bizarre way of looking at it. I'll show you how that works. It comes right out. Have a good day. Did you get the official? You get the whole, I don't know if you got.
I got that last
Oh,
one.
you did? Okay, sorry.
You're here last
You didn't get the whole, you didn't get the whole set.
So, like, it's lead it like, one. Oh, they kind of come back, right, and stuff. It's probably.
Yep, yep, somewhere up here, I guess.
Is there actually a distinct file?
I'll get
So the files are indistinct.
Now there is.